I'll go ahead and I'll start recording because every time that I tell people that stuff is easy, they always get into some subject that or some part of the AP Physics stuff that they kind of reach a snag to where it's just not quite the way that they think of it. So whenever I say that something's not as bad, that's a relative term because right, it's relative to me. So like if I say that it's easy, that does not necessarily mean that it's easy to somebody else. You know, it could be very, very difficult. So um, the, so there'll usually be at like some time in the year when we talk about like one specific subject where it just normally gets to you. So I can't necessarily say that kinematic equations are the hardest part. Um, it just is what it is. If I were to have my opinion on the hardest part, the rotational motion and torque are probably the hardest to conceptualize because when stuff starts spinning, our heads start spinning too at the same time. It's a little bit hard to wrap our brains around it. We did an example where there was an object that was moving down a ramp, and we did another problem where there was a guy falling out of a plane or a girl. I'll be gender neutral here. It doesn't really matter. They will both hit the ground at 22.6 seconds if there is no air resistance, and that's fine. But let's try a couple of other examples, things that are not as straightforward as what we had last time. So we're going to try to make our life's a little bit more tricky to where we're going to have to do a little bit more analysis in order to solve the problem. Um, the first one that we'll do is a classic hot air balloon problem. So there's a hot air balloon, and for some reason you decided to get in a hot air balloon, which is probably not the best idea that you've had in your life, but that's okay. Um, Only about 5% of ideas are good. So there's you in the hot air balloon. And it's going up this way. And you being full of bad ideas, you decide to just go ahead and take a ball and you just drop it. And we're going to say that this hot air balloon is initially going up at 5 meters per second. So you're inside and you just reach out and you drop the ball. Okay. And what we're going to be tracking is we're going to be tracking the ball and how far the ball falls. And we're going to say that it is right whenever you first start, your distance to the ground. It's a hot air balloon, so we can't go like super high. Let's say that we're about 150 meters. That's reasonable for a hot air balloon, I think, ish. So we're going to take that and we're going to like drop the ball from the hot air balloon. Okay. Now, if we try to think about the motion of what's going on, I think we might need more information to be able to solve this. I don't know. Let's find out. Let's see if we can find out how long it takes to hit the ground. And let's see if we can find the final velocity whenever it does actually manage to hit the ground at the end. We do know acceleration. So let's go ahead and let's think about what's going to happen with the ball itself. So the ball, what is its initial velocity? No. Yes. Okay. And because whenever you drop it, and this is going to be weird, okay? And if there was a person standing on the ground that you were trying to drop the ball on to like hit him in the head, which would be terrible, please don't do that. That's very unethical. But if they were looking at you, what they would see is they would see the ball go up a little bit before it went down. Because whenever you let it go, you were letting it go with a positive velocity because you and the ball had a positive velocity. So it doesn't start with an initial velocity of 0 meters per second. It actually starts with an initial velocity of positive 5 meters per second. Okay. And that means that it's going to, yeah, because it's actually going to go up a greater amount of distance, right? So a couple of other things that we need to think about is this 150 meters, is that a positive or is that a negative number? Are we going up or down? Okay, so which one are we focusing on? Are we focusing on the person or are we focusing on the ball? Okay, since we are focusing on the ball, it is going to start at 0 and it's going to go down 150 meters. So let's go ahead and give that a negative number. So negative 150 meters. It's going to go down and hit the ground. So let's write out our DVAT. We've got our distance, VI, VF, AT, and let's see what we have and see what kinematic equation will actually work. The distance is going to be negative 150 meters. Okay, the initial velocity is going to be positive 5 meters per second. And these positives and negatives make a really big difference in this problem. The VF is, I don't know. The acceleration, negative 9.8 meters per second squared. And the time is, I don't know. So we're looking at all of the different variables that we have. And we have a VI, we have a D, and we have an A. So is there any of the kinematic equations that would work for this? The third one? So the D equals VIT plus 1 half AT squared, this guy? Okay, so we have our displacement. Our displacement is negative 150. Oh, I did not write that right. The displacement is negative 150 meters. The initial velocity is positive 5. So notice we actually do have something here this time. And then the time is here. Plus 1 half negative 9.8 times the time squared. So as you guys can see, there is a slight issue here. There is a t and there's also a t squared. So we're going to have to deal with both the t and the t squared. And I don't think that this is going to factor nicely. So if we were going to try to use our FOIL method or something like that, 9.8 just doesn't really work very well. So the only reasonable option that we have to do is either complete the square or use the quadratic formula. So I think that's probably going to be what we're ending up doing to find the time is we're probably going to have to use the quadratic formula. But let's simplify everything first. And let's say, okay, we've got negative 150. If I simplify and I'm going to get rid of the units at the moment, positive 5 meters per second times t, that's really just 5t. And 1 half of 9.8 is minus, what is that? Is that 4.9? Okay, 4.9. And I'm not going to put the meters per second squared, t squared. All right, solving quadratics 101. What do I need to do? Yeah, that's the quadratic formula. So I'm going to go ahead and write that one out. So which you can remember by singing "Pop Goes the Weasel" to it. Negative b plus or minus square root b squared minus 4ac. Have your math teachers never sung "Pop Goes the Weasel" to? Never? Oh, but it's here you go. Ready? X equals negative b plus or minus square root b squared minus 4ac all over 2a. Now you're never gonna forget it. So it's done now. It's been seared into your brain. I'm sorry. Yeah, I always sing to my algebra students because I don't know, it just makes it less traumatic. I'm not really sure what to say. So you can use that. There's your quadratic formula. And digital students, I'm sorry, you're now traumatized for life. Um, so the x in this case is the quadratic part. That's the t. And the a, the b, and the c only work if we set everything equal to 0. So let's write this in like the actual order of a quadratic. So the squared goes first. So it would be negative 4.9 t squared is the first thing. That's the a term. The b term is the plus 5t. And the c term is going to be plus 150. And that's going to equal 0. So if you write it out like this, you can get your A, your B, and your C. I don't know if my highlighter is working today, but oh, it is. This is going to be A, it's going to be B, it's going to be C. All right, so A, B, C. So it's going to be, I'm not going to write X this time. Let's write it as T since this is the variable that we're using for the equation. T equals negative B, so it's going to be negative 5, plus or minus the square root of 5 squared minus 4 times negative 4.9 times, crap, I ran out of square root room. Let's just make it bigger. C, 150. And then the square root ends on top. The whole thing is divided by 2 times negative 4.9. Okay, calculator time. Because if you say that I can do that in my head, you crazy. That's not the case. So we're going to do negative 5 plus all that crap, and then negative 5 minus all that crap. I highly recommend you guys try this out. I'm going to need a answer, and I'm also going to need someone to second that answer. Keep in mind you're going to get two of them. One of them is not going to make sense because one of them is going to give you a negative number. That stands for negative time. And the arrow of time only goes forward. So we're going to ignore the negative answer. Hopefully we'll get a reasonable positive answer. Try putting that into the calculator. Um, we may need to simplify some stuff out before we throw it in the calculator, depending on how skilled we are with it. The positive ended up being negative 5.04. We're going to need a second on that. So it's negative 5.04. I'm just going to write down some answers that you guys are giving me. Seconds. Okay. You got negative 5.04. There's a second on that one. Y'all, everybody else make sure that we get negative 5.04. So since that's the negative one, I'm inclined to believe that that's the one that we're not going to end up being used on this quadratic. Hopefully the other one turns out to be a positive number. 6.06. Okay. Okay, that's fine. Y'all take your time. So the second one and 6.06 seconds, and I have that one, and I have a second. Okay, so with the quadratic formula, we found out that there are two solutions to this, one using the positive route, one using the negative route, and we're going to disregard this answer because since that's the negative solution, that's what it would have done if it would have gone all the way over on this side. Okay, so like if you would have started originally to make it up to here, that would have taken 5.04 seconds. But since that's negative, that means that that's already happened. So that time is negative and doesn't really apply to us right now. Does that make sense? Yeah, so like 150 meters is a large distance, right? So you're covering like a tenth of a kilometer, and you're doing that in about 6.06 seconds. Is that a realistic amount of time? That is not a realistic amount of time? Well, no, 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 no. We can't. We're not going to shrug. We have to judge whether or not this is realistic or not. We can't be like, it's fine, because this is physics class. This is what we're doing. We're trying to calculate it. What is reasonable then? I don't know. What is? Let's. You're right. You're not, and we're not going to calculate air resistance. We'll tell you what. Is the acceleration constant? Okay, so if the acceleration is constant, we can safely make a velocity time graph, right? Okay, so why don't we just make a quick sketch of a velocity time graph to see if this actually makes sense. So I'm going to make a velocity time graph, and we're starting at, so like basically the velocity time graph is going to go down, right? Why did you do this? Because this is just the way that I roll. I don't know. Velocity time, because we need to be able to like visually justify whether or not our answers are correct or not, or else we're basically just doing math, and physics is not really math, it's applied math. So it's math that makes sense, and engineering is applied physics. Yeah, so absolutely. All right, so we have let's see, after 6 entire seconds, that's going to be 6 this way, right? So do we know what our velocity is after 6 seconds? About 60 meters per second. You know how I know that? Okay, yeah, because we're accelerating at 10 meters per second, right? So after the first second, we're going 10 meters per second. After the second, we're going 20 meters per second, then 30, then 40, then 50. Then we get down to 60, okay? So we are doing, what is 6 times 6? 60 times 6. 360. Okay, so that's 360, and this is, I'm doing an area. This is a triangle, right? So what's half of 360? Okay, so now since I'm kind of guesstimating here, so there is a 6.06, and gravity is not quite 10, it's 9.8, so hopefully that gives us a little bit less distance. But yeah, this is that I get it. We're starting with a positive velocity. So this is an example of just starting at 0 and moving down. So since we have a positive velocity, it's going to take us a little bit longer. So we cover a smaller vertical displacement. So yeah, this is a reasonable answer. Just by looking at a velocity time graph, this is reasonable. It's not going to get us exactly the same thing, but we can just draw a simple triangle and say, oh, hey, doing the area under the curve, I can figure out that the displacement is going to be pretty close to 150. So I think I think we did good. I think we've got it. I think this is a reasonable answer. So the time for the entire duration ended up being 6.06 seconds. We can use that information to find the final velocity and anything else that's missing. Was there anything else missing besides final velocity? I got rid of my DVAT. I can only see part of it up there. I see VF and I see T. Okay, so if we just need to find VF, so this is time, and I'm just going to go ahead and box this one in. This is the appropriate amount of time. What would I use for finding the final velocity? Okay, that's the easy one, right? Because at this point you have two options. You could either use VF squared equals VI squared plus 2, I'm keep writing it, plus 2AD, right? You could use this, but there's squareds here. So if you can avoid it, try to avoid it. So if we look at the other kinematic equation, that's VF equals VI plus AT, that we have time, we have acceleration, we have the initial velocity, we can use this one. So let's pick it. Okay, so VF is equal to 5 meters per second plus negative 9.8 times our time of 6.06 seconds. And let's see, I guess we need to multiply these two together first. I don't know why I randomly start writing in units. So negative 9.8 and 6.06. Randomly have these come together. Is that for the right side or the whole thing? The whole thing, what'd you get? Negative 54.388. Let's go ahead and make that negative 54.4 meters per second would be the final velocity. Now, does that make sense that it is a negative number? Yeah, that makes sense that it is a negative number. Did it come out to be about negative 60? So we had a fall of 6 seconds, right? So if it was just starting at 0, it would have been 10, 20, 30, 40, 50, 60. But since it had a positive velocity of positive 5, that means it went 5, negative 15, negative 25, negative 35, negative 45, negative 50. Oh, wait a minute. Did I count way too many? I think I just counted like 7 times. I don't know. Hang on here. We're a little bit we are 5 meters per second lower than 60, okay, which is a good indicator that we got the answer right because we started off with a positive velocity of 5 meters per second, okay? Does that kind of make sense? So I believe that this answer is a reasonable answer, and physically it makes a lot of sense to me. So I think that this is, and it's always good to double check yourselves. You can double check yourselves by checking the units and making sure that they're okay, or by physically just like thinking about the problem and using that velocity time graph. Because whenever you got free falling objects, you can easily calculate your speed. 10 meters per second increase for every second that it falls. That's a good way to eyeball how fast you're going to be going. And it also applies the same way if you have an upward velocity. It just subtracts 10 every single time until it reaches 0. Then it starts going down faster. So if you started with a speed of positive 30, it'd be positive 30, positive 20, positive 10, 0, negative 10, negative 20, negative 30, negative 40. And it just keeps going down like that. Okay? Does that make sense? Okay. You want to try another one? I think we got enough time to try another one. Okay. let's see. I'm trying to think of a different situation because I don't want to do the same situation every single time. And I'm trying to think of like all the situations that you might encounter in the homework. Um, I think we've done some where we did acceleration. Why don't we try some where we do a negative acceleration? So how about do what? Gravity is a well, no, 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 no. Okay, let me rephrase because like negative acceleration can go two ways. In gravity, we have a negative acceleration, and the negative acceleration is speeding up, right? Let's do a negative acceleration where it's slowing down. So let's do the aircraft carrier. So if you are oh that's crooked. Hang on. Let me try again. Let me try again. It's a broken aircraft carrier. Yeah, $250 million right here. That's it. Okay, so you got on like an aircraft carrier, right? And there's a plane. This plane is over here. This plane needs to land on the aircraft carrier. Okay. Do you need me to draw the plane? You need me to draw the plane. Listen, this is gonna visually help you. You're gonna get visually helped right here. This is an F-15 fighter that is uh costs like 15 times more than my soul. There we go. That's it right there. It's also got another wing to the other side of it too. There you go. This airplane needs to land on the aircraft carrier, and the distance that the aircraft carrier is cannot be extended. Like you don't have the magical extender aircraft carrier edition. Like what you got is what you got. So let's say that the aircraft carrier only has a distance of 100 meters, which is actually a pretty small aircraft carrier. It's the little boy version. Okay? And the airplane itself is traveling at a positive velocity. We're only going to worry about the horizontal. Let's not worry about the vertical to keep things like simple. We're going to say that this airplane has a velocity of 150 meters per second, which is about 300 miles per hour. So this thing is booking it pretty fast, and it needs to land on this aircraft carrier. And what we need to find out is this thing has to decelerate. This thing, I said the magic word. This thing has to negatively accelerate. It accelerates in the negative direction, and it's going to have to do that at such a rate. So we're going to have to find out what that negative acceleration is so that it can actually land on the aircraft carrier and not accidentally go over. Okay, so normally what engineers do is they like test the stuff beforehand. They're not just like, oh, go try it out. That's normally not what happens. Okay, do you want me to change that? The smallest aircraft that existed according to Google is 182 meters. So there we go. The Google has spoken. So let's just change that 100 to be more realistic and we'll use 182. I'm fine with that. Okay, so we'll switch it over to 182. And from here, here's what we'll do. We need to use our kinematic equations, but do we have enough to be able to solve for what we need? Let's write out our DVAT and let's see. Do what? That would be preferable, right? Like we would very much prefer that the final velocity be zero. We don't want to have a velocity once we reach the end of the aircraft carrier. So when we write out our DVAT, the D is equal to 182. The VI is positive 150. The VF, preferably, is 0 meters per second. I agree. The acceleration is, I don't know. And the time is, I don't know. So it actually doesn't give us either one of those. So can we actually figure out what the acceleration and the time is using distance and initial and final velocity? We can use the forbidden fourth kinematic equation, which is, what is that? Distance or displacement is equal to VI plus VF over 2 times time, and that'll let you find the time, correct? Okay, now warning, this is not on the AP Physics formula sheet, so you must memorize that if you want to do it this way. So that is fine by me. So let's try this. The displacement is 182, and that's a positive displacement. The initial velocity is 150. plus 0 divided by 2. All of that times the time. So that comes out to be, let's simplify a little bit. That's 182 is equal to 75. Oops, that's not 75 over 2. That's actually just 75. So it's just 75t. So that means that this thing is going to have to stop in 2.42 seconds. Fantastic. 2.42 seconds. That is a lot of G's, and ideally, you would really not have a airplane try to land at this speed. It would not be a good idea. You definitely want it to go slower. But at least we're looking at this and be like, you know what? If it's going that fast, this physically makes sense. It's going to have to do this in 2.42 seconds. So if it needs to do it in 2.42 seconds, which we can write that on the DVAT, so I'll erase my question mark and I'm going to write 2.42 seconds. Um, Yeah, basically you just like hit the ground and uh a lot of times what they have is they put cords up there, so like whenever they land, the cords grab it and like yank it back so that it like doesn't just rely on its wheels in case it doesn't stop. Yeah, you can reel them back in, worst case scenario. God, I hope that wouldn't happen. So what kinematic equation would we use to find the acceleration? That's usually the easiest one. So if you can use that one, I would definitely use it. The VF equals VI plus AT. If you can get away with using that, I would. So I think we can do that. The VF is 0. The VI is 150. The acceleration is I don't know. And the time is 2.42. That actually works out really nicely. Um, it does. Because we can move that 150 over to the left side. We can subtract 150 on both sides, and that gives us 2.42 times a. So we'll just take the acceleration and divide it by 2.42, which would give us a value of, yeah, negative 150 divided by 2.42, negative 61.22 meters per second squared. This is survivable. Uh, Obviously, acceleration due to gravity is 10 meters per second. So this would equivalently be roughly what we would call 6 Gs. Okay, so like if you think about like how many times you would multiply yourselves by Earth's gravity, you can think of that as a G. So negative 61.2 meters per second would be 6 Gs, and that is normally what they subject astronauts to during training, is gravity accelerations that are equivalent to about 6 times or 7 times the acceleration due to gravity of Earth. I don't know specifically what number they make them push the limit to, but I know military pilots have to go through these G trainings because if you are subjected to it for a really long time, you start to pass out. Okay, you start getting sleepy because you're not getting all that blood flow up to your brain because you basically feel 6 times heavier than you do. So if I weigh 200 pounds during this type of acceleration, I would feel like I weigh 1,200 pounds. So you can't really sustain yourself very long like that, but you can survive. You would live. So about 5, yeah. After that, you start getting like it's sleepy time. Uh, who? Yeah, yes, yeah. Like once you get to a specific location, like you have to train your body to know how to deal with that kind of stuff. So normally, like if you got around 5 Gs, you'll actually start passing out. And if you look at videos on YouTube of pilots going through this training, when they get to that point, like they just like lights out. Like they'll just like slump over and they are OUT out. Okay, so survivable for 2.42 seconds. Probably not ideal though. So most of the times we make the aircraft carrier a little bit longer so that you don't like go crazy hitting the ground. Yeah. Yes, you have to be wearing a special suit. Like fighter pilots can sustain like have to sustain 8 or 9 Gs because of the combat turns. Like they don't normally subject themselves to that, but when there's something firing at you, then you definitely want to be able to turn very quickly. Yeah, very quickly. Roller coasters I think only go to about 3 or 4. Well, yeah, you can design a roller coaster that could kill someone, but you hopefully aren't gonna build a roller coaster that would kill someone. But how much time do we have left? We have a little bit of time, so I think we can try and actually, I think I'm just gonna open the homework to you guys. So I think from here, if we need to work on a specific homework problem, we totally can. But I'm gonna open it up so that you guys can work on it. I think we've had enough examples that we can see how the kinematic equations work. Um, and we'll try to work on this and we'll answer questions that you guys have on Tuesday. So I'm just gonna open it up to you guys and we'll work with it from there. Digital people, have fun.